Hello and Namaste. This is Kalyan Chavan. I am here to present my work. The title of my work is Structural and Optical Investigations on Direct Current Magnetron Sputtered CZTS Thin Film. We know that energy is a basic principal need of a mankind, and on earth we have major source which we are using, that is basically petro source, but it has limitation. So we have to search a new kind of source, that is renewable energy source, and in that, on top in that list, there is a solar energy. Solar energy is one of the major renewable energy source. But in order to harvest solar energy, we need thin film solar cells. There are different generations of solar cells. In first generation, if I talk about first generation, there is a silicon based. In second generation, for example, there is a CIGS, copper, indium, gallium, sulfur. And in third generation, we have a best candidate, that is CZTS, that is Cu2Zn SnS4. It is a basically it works like a best quality solar absorber layer in thin film solar cell, because if I look at the composition of CZTS, almost all elements are non-toxic, so they are eco-friendly, and since all elements are earth abundant, so the cost wise, if I compare this material with other one, so it is more cheaper. So it makes this material more superior as compared to previous, which I have told you. Now in this investigation, I have grown CZTS thin film on soda lime glass by using DC magnetron sputtering. These deposited layers are probed using X-ray diffractometer and UV visible spectrophotometer in order to investigate structural and optical properties respectively. In addition to that, I have done Rietveld refinement in order to look in structural aspects of what my deposited CZTS layers. In experimental details, first of all, I have cleaned my glass substrate using double distilled water, IPA and chromic acid. These cleaned glass substrates were assembled in sputter chamber. CZTS quaternary target having dimensions which are there in front of you, and it is 99.95% pure. I have assembled in sputter chamber. This experiment which I have planned, it is carried out at 4 different deposition temperatures or substrate temperatures, you can say, from room temperature to 400 degrees Celsius in the steps of 100 degrees Celsius. These depositions were carried out in argon ambient. The flow rate of argon during the deposition, it is 80 SCCM. It is maintained throughout the depositions. Deposition time I keep constant for 20 minutes, and throughout the deposition I have used direct current, that is DC power of 50 watt. This is what first characterization. This plot shows us or depicts us, or it portrays us basically X-ray diffractograms of different layers which I have deposited using DC sputtering. If you look at A, B, C, D and E, it is very clear that as I go on increasing the deposition temperature, there is a enhancement in crystallinity of grown layer. Not only that, if you look at carefully, graph C, D and E, one can easily notice that there is a change in preferred orientation. So if you compare plot E with plot D, it is very clear that in plot E most of the crystallites, they grown themselves along 112 plane. On the other hand, in case of D, you have or we have dominating 220 plane. So what this indicates? It indicates that not only we have got increase in crystallinity because of increase in deposition temperature, but also we have preferred orientation. This one can use while growing or while designing solar device or thin film solar cell. Now this is what the X-ray diffractogram. Now by using this X-ray diffractogram, I have calculated crystallite size and dislocation density by using Scherer formula, and from Scherer formula I have obtained crystallite size, and by using crystallite size one can easily find out what is the dislocation density. There is a formula, one can easily tell what that d delta, that is dislocation density, is equal to 1 upon d square, where d is a crystallite size. Here if you look at the graph, it is very clear that upon increasing temperature, substrate temperature, there is an increment in crystallite size. Why this happens? It is very obvious that since in order to grow bigger crystal, a energy is required, because when you deposit a material using sputtering, whatever the add atoms which are basically stick, or you can say which are basically collected on substrate, they need energy to come closer or to grow bigger. So using this thermal energy, using this temperature, basically this temperature assists to that particular process. On the other hand, when I say crystallite grows bigger upon increasing temperature, definitely whatever the dislocations are there, whatever the voids are there, they will basically, they are going to decrease. So this plot depicts exactly what I have told you. This is the top plot. This plot I have plotted using UV visible spectrophotometer. Here you can see here different plots I have clubbed in a single chart. On x-axis I have energy, on y-axis I have alpha h nu square, since it is direct band gap semiconductor. Now if I look at this plot and if I go for the band gap calculation, it is very clear that band gap decreases with increase in temperature. Why this happens? The reason is very simple, because as temperature goes on increasing, there is an increment in crystallite size. So when there is an increment in crystallite size, it will lead to quantum confinement effect. And definitely a result of this quantum confinement effect appears in the form of decrease in band gap of a material. So it means that you can change a band gap of deposited layer, you can vary the band gap of deposited layer by using this process control parameter, which we call substrate temperature, right? And see, if I look at this variation in band gap, and if I compare these values at different substrate temperatures with this previous graph, say basically both these graphs, they basically assist each other, because here upon increasing temperature there is a increase in crystallite size, and this next graph, it shows us upon increasing temperature there is a decrease in band gap. Basically band gap decreases because of increasing crystallite size. So this is what the top plot. Now here we have result and conclusions. No doubt along with these few slides I am going to put more detailed refinement. No doubt I am going to use Williamson Hall method to find out a microstrain to find out crystallite size, but because of lack of time, there is a time limitation, so I have avoided most of the slides. So here the resultant conclusions. Number 1, in this investigation, CZTS thin films has been deposited using DC magnetron sputtering on glass substrate at different substrate temperatures. These deposited layers I have analyzed using XRD and UV visible spectrophotometer. X-ray diffractogram depicts that deposited layer possess tetragonal crystal structure, and if I compare the X-ray diffractograms of these layers, it is very clear that as deposited thin film, that is deposited thin film at room temperature shows a pure amorphous nature, but upon increasing substrate temperature, there is an increase in crystallinity of thin film. Not only the crystallinity of thin film increases, but also there is a change in preferred orientation. So one can say, using this kind of methodology, one can have controlled growth of preferred orientation. Along with basically here, by using talk theory, by using talk plot, I have obtained band gap of CZTS thin film, and that plot shows us there is a systematic decrement in band gap with increase in substrate temperature. This is all about the investigation which I have carried out. Thank you. I will be happy to answer your questions if any.